We're still working on geometry for G8, and today we were talking about volume. We started with review for the volume of a box or a rectangular prism. So essentially, we started with a mental exercise. If the room was 20 by 10, how many square blocks? But that started to get confusing, so it was all in our minds. So we pulled out things that we could actually see and manipulate. So if we have a box that's 2 by 3, these are 1-inch cubes. You could also just use your 100 blocks, like the blocks themselves, or wooden blocks would work fine, or even if you've made trouche blocks, you can use those. 2 by 3, and that essentially gives us 6, right? When we're measuring area, we measure in squares. When we measure volume, we're measuring in cubes. And so this is our first layer, and our area and volume are the same because this is 1 inch tall. But if we go up to 2 inches, then we need another layer, and 3 inches would bring us yet again another layer. And so it becomes really clear that to calculate volume, we're calculating the area, length times the width, and then moving up towards the height. So this is review, and I always back up a little bit so I know that the concepts needed for the understanding of what I'm going to teach are there before I start teaching it. But also I am presenting it in this way because this is how we're going to derive the formulas for other prisms and then look at other solids. So there's that. And then we went into finding the area of these prisms, which is essentially finding the area for the shape at the ends and then multiplying that by the height. So we did that for this, and we did this for the cylinder in addition. And then we started looking at relationships between a pyramid, this kind of pyramid, the Egyptian pyramid, that has the square as a base. And then we also talked about shear and stretch. Shear and stretch, like this was a rectangle, and we cut it up into tiny little pieces this way, and then we move it along this way to show that the area of the parallelogram has the same area as the square, the height times, or not the square, the rectangle, height times the base, right? So I wanted to remind her the shear and stretch. So when we move this pyramid over to the corner for this demonstration, let me pull, wow. See, these are our tilted pyramids. Now, this is not actually our pyramid. Our pyramid would actually be as tall as it is wide and long, right? Because this is a cube. But what we have done is moved that top of the pyramid over to the side of the cube, and that creates a tilted pyramid. Because we can assemble these, which she did very quickly, but it takes me a few minutes, so that 3 of them make a cube. If I didn't mention, this is from Jamie York's Making Math Meaningful in the middle school grades, and he has nets for these. If you need help deciphering those, let me know. And it provides a cube. So we know that the volume of a pyramid is 1/3 of that of the cube that it fits into, or the cube of the base, right? Okay, then we went into the relationship between a cone, this is wet from our demonstrations, a sphere, and the cylinder. I did not have the cylinder available. The cylinder that would be the same circumference and height. And that was a little bit confusing to her that I didn't have it. So something similar to this, right? It would have a circle at the top and the bottom, and that would be the same circumference of the sphere, and the cylinder would be the same height of the sphere. So we're looking at the relationship between the cone, which also has the same circumference at the base, and the height of the sphere, and the relationship of the cylinder. So these three items. And what we did initially was to calculate the volume of the cylinder, because we had already done that with these prisms. So we did that first. And then we used water displacement from our work in chemistry. So what I did here was fill it up to 150, and then we took the ball and placed it in and held it down to see how much water was displaced, just right here. And then what we're going to do is then remove the 150 from my beaker, because that is what we started with, and what we're left with is the volume first I have to fill this up to the line, and it's the difference between those two that is the volume of the sphere. So first I take out 100 because my cylinder only goes to 100. And then I take out 50 more because that's what I started with, 150. I needed enough to make sure that the ball was going to fit under the water. And that means this is how much water was displaced when we started, which we calculated at roughly 65 millimeters, and water is 1:1. So that's, it's a little over here, but it was roughly 65 centimeters. Water's 1:1 cubic centimeters. So that gives us roughly 65 cubic centimeters. So our calculation here for our cylinder was roughly 98, and our sphere was 65. When we divided those, we found the relationship to be like what fraction of the sphere is the cylinder. And when we are demonstrating this, we can clearly see that the sphere only takes up a portion of the cylinder. So what portion is that? To get that portion, we're dividing 65 by 98, and it gives us 0.666, which we know from our math work is 2/3. So we know that the sphere is 2/3 of the cylinder. And then we're looking at what is the relationship between the cone and the sphere. Now you remember, I'm going to pour this out a little bit. So then what we did was take, this is our volume of our sphere, and we are going, this is already wet, so I don't know how this is going to do. We pour how many of these into our cone? And the cone was a little tricky for me to make, but essentially 2 of these will fit into our cone. The relationship between a sphere, a cone, and an area, so cone to sphere to cylinder, is 1 to 2 to 3. So we figured out that this was 1/2 of this, or this is double this, and this is 2/3 of this. So 1/2 of 2/3 gives us 1/3. And that is how we established the ratio for this. And now we have formulas for finding the volume of a sphere. You essentially take 2/3 of the volume of the cylinder, and the volume for a cone, which is 1/3 the volume of the cylinder. And that was our math today.